Hi everybody, in this video I'm going to go through our lesson on centroid and orthocenter. And to begin this, I want to first talk about what a median of a triangle is. It's the median of a triangle. So remember, we have like the circumcenter and the incenter formed by perpendicular bisectors and angle bisectors. Your medians also form a point, and a median specifically is the segment from a vertex to the midpoint of the opposite side. So here I'm going to just draw a little triangle, and I can find the median, right, of this triangle. Any side has a median. So I'm going to find the median of, let's say, AC, the bottom side. So that is going to go through the midpoint of AC, we'll call that M, and the opposite vertex. So it's the segment between the opposite vertex and the midpoint. So AM is congruent to MC. And MB here is the median. All right. So your triangle has three medians, and those three medians form the centroid. Oops, let me write that a little better. Centroid of the triangle. Whoa, okay, that's fine. That's fine. So your centroid of a triangle, that is the point where the three medians intersect. And this point is sometimes known as the center of mass for the triangle, or the center of gravity within that triangle, because we could balance the triangle on that point. And that's why it gets that name. And it will always be inside the triangle then. So always inside the triangle, in the center. So let's kind of draw an image of a centroid. Here is a triangle, and we are going to have to find the median really of all three sides. So this can be A, B, C, and we'll start with AC again. So I always like to find the midpoint first. So midpoint of AC maybe is like right here. Oh, okay. So this would be point M, and it'll connect with point B on the opposite side. All right, now I can do AB. So midpoint of AB maybe is like right here. We'll call that point N, and it should connect with the opposite vertex, C. So here is our other vertex. Now, I mean, the intersection here is the centroid, but let's find the final median from vertex A to BC, and midpoint looks like right there. This can be point O. So these three medians all intersect at this common point P, which is our centroid. Now, because these are medians, all of the sides now have been bisected. So on the bottom side, AM is congruent to MC, AN is congruent to NB, because that side's been bisected by the median, and OC is congruent to BO. So this centroid is always inside, that's the center of mass, and with this we have the centroid theorem. So the centroid theorem states that the centroid of a triangle is 2/3 of the distance from vertex to the midpoint of the opposite side. So this centroid, this point P, that is 2/3 of the distance from vertex A to the midpoint of the opposite side. Oh, so this is saying here, AP, the distance from the vertex to the centroid, is 2/3 the distance of the entire median. AO. If we think about this kind of logically, I always like to think about it by just like drawing out a straight line. So here is segment AO. Here is A, and that is our vertex. And here is O. This is the midpoint of the opposite side. We then have the centroid, right? We have P right about here. And this is 2/3 of the distance, which means that from P to O, that's the remaining 1/3 of the distance. So AP, that is 2 parts, right? That is double the length of PO. So the centroid to the side, that is shorter, right? Versus the centroid to the vertex, that is 2/3 the length. And then the entire length, that would be 3/3. And we could say the same thing, right? Like BP, that is 2/3 of BM. And then I also should write that PO is 1/3 of AO. That's something we can kind of come to find. Now, let's also talk about altitudes because your triangle or triangles can have altitude. So what is the altitude of a triangle? And when you hear altitude, please think height. It really is the perpendicular segment from the vertex to the opposite base. And that really, when I say base, or you see base, that's talking about a side. So let's just draw a kind of generic triangle here. In this triangle, we can find the altitude. This is A, B, C. I can find the altitude from any vertex to the opposite base. So if I want to find the altitude from B to AC, that is the perpendicular distance from B down to that side, right? So that would just be straight down to AC. So this point D, BD here is the altitude of this triangle. This is altitude BD. We could find the altitude from C to base AB or from A to base BC. It is a little bit funky though when you have an obtuse triangle. So let's see how I do drawing an obtuse triangle. So this will be ABC, ABC. And if I want to find the altitude from point B to this opposite base, which is AC, well, if I just draw a straight line down, creating that perpendicular segment, well, when will it intersect with this side? We have to extend the side further to find where it will intersect. So here, if we extend side AC out further, then I can construct the altitude from B perpendicularly down to AC. So now maybe I have this new point over here, D. So I have altitude BD, which is inside the triangle for our acute triangle, but in our obtuse triangle, this altitude was outside. BD is the altitude from B to base AC, just measuring the distance, right? Between the level AC is at and the level B is at. So some quick notes here on this. When you're looking at an obtuse triangle, altitudes may be outside. Some of them will be, but some might not be. And then, ooh, I don't know, there we go. In a right triangle, the two legs are two of the altitudes. So two of your altitudes are the sides of the triangle. And we're going to look at that in just a moment. So bringing this all together, what then is the orthocenter of a triangle? Perfect. The orthocenter is the point where the three altitudes of the triangle intersect. So this could be inside, it could be outside, or it could be on the triangle itself. Let's talk about the difference. How do you know? So let's start with an acute triangle first. So in an acute triangle, your orthocenter will always be inside the triangle. So let's draw an acute triangle. And if we're going to find the orthocenter, right, this is going to be finding the altitudes of each side. So perpendicular height from this vertex I just highlighted in dark green. Let's see, let's give these names. A, B, C. So from B to AC, we can construct that height. It's not perfect, but it'll do. I can construct the height from A to BC. So let's see. Maybe it'd be like so. Oh. And then our final altitude would be from C to that side AB. And it should intersect, right, the other altitudes, which it does. So here I have our orthocenter, which is inside the triangle. All right, let's now look at an obtuse triangle. So in an obtuse triangle, your orthocenter is going to be outside of the triangle. Let's draw an obtuse triangle. All right, so, and give it a name, A, B, C. I'm going to start with the altitude from C to AB, because that one's the easiest for me. It will be inside the triangle like so. Kind of. And I'm just going to warn you, it's outside. We're going to have to extend this altitude farther. So sometimes you will have to imagine, your altitude goes, it's a line too. So we could extend it farther because it's not going to be inside the triangle. It's just the line that contains the altitude essentially. Now let's find the altitude from B down to AC. So I'm going to extend side AC further, and I'm going to do that in gray. So now I can find the perpendicular distance from B down to this side. And then I can extend it even further. And now we have an intersection point. And then I can do the same thing for side CB, right? I can find the altitude from A to CB, but that's going to require that I extend CB. So let me extend CB down some more. It's not perfect, but it's okay. And this one actually has to extend a little bit if I think about it. And I will draw now my perpendicular line from A down to this extended line. And I'm gonna have to extend it. And it should, I kind of messed up because I'm doing it by hand. It should meet where the other ones do, but I clearly messed up when I was making all of these little dots. I think that kind of messed things up. So let's just take it from here again. Yeah, I think I made the slope kind of messed up. So let's see, it should be something like so. So your orthocenter is where your altitudes will meet. And in an obtuse triangle, you have to extend the altitudes so that they meet outside of the triangle, and it will be extended past the angle that is the obtuse angle, right? Here's the obtuse angle. All right, last case is if it is a right triangle, and these ones are special. In a right triangle, your orthocenter is the right angle's vertex. So it's the vertex that has the right angle, essentially. So let's draw a right triangle here. Or not. That's fine too. Why is it not doing the thing? Okay, so I'm going to find the altitudes, and I did not name this. A, B, C. First altitude I will find is from A to BC. So perpendicular from A to BC would be something like this probably. And then if I'm going to find the altitude from B down to side AC, well, this is a right triangle, right? So this is a right angle. So the altitude from from B to side AC would be this side itself. It would be side BA. That's an altitude. And if I'm finding the altitude from C to side AB, that would also just be this side. So the two legs are also altitudes, which means that this point right here that has the right angle, this is the orthocenter. And I didn't note where it was in this image. Here's our orthocenter. So it's outside. All right. So let's look. We have two examples here. And the lesson images are in the OMHS. You can either print it or take a moment to just put it in your notebook. It wouldn't take much. This is our image. It's a right triangle with all of these markings. And there are two parts to this. Psych, there's three. Part A, in triangle ABC, CP equals 8. What is CD? And notice no lines saying these are segments. We're talking about the measures. Now, what I want you to notice is we have all these lines going through the middle. And if I pick one of these lines, like CD, for example, D is bisecting, right? This segment AB, it's bisecting this side and it goes through the vertex. That's what the other lines through the middle do as well. So this tells me then, and this is important for this entire problem, that P is a centroid, which means that P is 2/3 of the distance from the vertex to the midpoint. So we know right now that CP from here to here, that is 8. And we want to find the entire length of CD. So let's first start off by saying that CP from vertex to centroid, that is 2/3 of the entire segment CD. And we know CP is 8, right? So 8 is 2/3 of CD. The easiest and most straightforward way to solve this for CD, right, to figure out what CD is, you could multiply both sides by 3 and then divide by 2, but that's really the process of taking both sides and multiplying it by 3 over 2. So I'm going to multiply both sides by 3 over 2. So that way, if I'm looking at the right-hand side, the 2/3 and the 3 over 2 will cancel, and we'll have just CD is equal to whatever 3 over 2 times 8 is, and that's really 8 over 1. So 3 over 2 times 8 over 1 is equal to CD, and simply multiply across the top and across the bottom. So 3 over 8 is 24, and 3 times 8 is 24, and 2 times 1 is 2. So I have 24 over 2, which is 12. So the length of CD is 12 units. All right, let's do B, part B. Ooh. In triangle ABC, BF equals 21. What is PF? So BF from B to F, so this entire distance is 21. And we want to find just from P to F, right? So I want to find the little piece of the entire whole. And when we have our vertex and our centroid and this other midpoint on the opposite side, the centroid is 2/3 the way down, right? So from centroid to midpoint, that is 1/3 of the total distance. So I can say here that the little piece, PF, is 1/3 of the entire segment, BF. So I can substitute, right? We know BF is 21. So PF is equal to 1/3 of 21, and multiplying 21 by 1/3, which is the same as dividing by 3, PF then, is 7. All right, last one for this problem, and then we're going to do one more. If AP equals 3x minus 3 and AE equals 6x plus 6, what is x? So just move this ever so slightly. AP is 3x minus 3, and that is from A to P. So that is 3x minus 3. And we know that AE, which is the entire segment, that is 6x plus 6. So the entire thing is 6x plus 6. And I want to remind you that the centroid, right, the distance from the vertex to the centroid, that is 2/3 of the whole. So this AP from the vertex to the centroid, it is 2/3 of the whole, AE. So AP, that is 3x minus 3. And that is equal to 2/3 of 6x plus 6. And now I can distribute the 2/3. You can, it's just a number. So I'm going to distribute the 2/3 to the 6x and to the 6. Nothing changes with the other side. So I just still have the 3x minus 3. And that is equal to, and now I have 2/3 times 6x plus 2/3 times 6. And I'm going to do a little scratch work off here to the side. 2/3 times 6 is like 2/3 times 6 over 1. So multiply 2 times 6 is 12, and 3 times 1 is 3. So this 2/3 times 6, that's really just 12 over 3, which is 4. So with that in mind, now I know that instead of having 2/3 times 6x, well, that's just really 4x, because 2/3 times 6, we know that's 4, plus 2/3 times 6 is 4. So just multiply 6 by 2/3, and then the x is a part of one of the terms. So now I have 3x minus 3 equals 4x plus 4, and I can solve for x. And first thing I'm going to do is I'm going to get my x on one side. I'm going to move the smaller x over. So I'm going to subtract 3x from both sides. And then that will get me -3 equals 1x plus 4. So now I can subtract 4 from both sides. And this will get an answer of -7 is equal to 1x. Please let me know what questions you have on all of the lessons that we've done so far, and I look forward to seeing you in class.